Welcome back to The Explainer. Today, we are unpacking a genuinely fascinating CVPR 2025 paper titled Vision Language Models Do Not Understand Negation. Have you ever wondered why state-of-the-art multimodal AI sometimes completely ignores the word not in your prompts? Well, today we're going to break down the architectural blind spot that's causing it.
Here is our cognitive roadmap for today. We'll start with the core negation problem, look at the new NegBench benchmark, dive into the author's data-centric methodology, review the experimental results, and wrap up with a critical analysis of where the field goes next.
Okay, let's jump right into Section 1, the negation problem.
Now, you know modern vision language models. We're talking about giants like Clip, Blip, or Lava. They perform incredibly well on standardized exams and complex visual question-answering tasks. But surprisingly, these massive models stumble on some of the most basic compositional reasoning out there. Specifically, they fail to recognize the absence of an object. So the real question is, do they actually understand what isn't there?
Picture this real-world scenario. You prompt a standard retrieval model like Clip for a picture of a dog, but not on grass. What do you get? It confidently retrieves golden retrievers sitting right on a bright green lawn. It semantically understands dog and it understands grass, but that logical constraint, the word not, is completely ignored.
To understand why this happens, let's do a quick refresher on how these models are trained. Models like OpenAI's Clip use contrastive learning. During training, the model processes massive amounts of image and text caption pairs. Its whole goal is to create embeddings, which are basically mathematical representations in a shared high-dimensional vector space. It pulls the embeddings of matching images and text close together and pushes the non-matching pairs far apart.
And that training objective essentially turns the model into a highly sophisticated bag-of-words pattern matcher. Standard image text retrieval relies heavily on this simple semantic overlap. But true compositional reasoning, actually understanding the strict logical constraint that a specific object must be absent, well, that requires a much deeper syntactic comprehension, and simple pattern matching completely misses that nuance.
So, how do we measure this gap? That brings us to Section 2, building the NegBench benchmark. The authors posed a really crucial research question here. Exactly how well do current VLMs comprehend negation across different contexts? Now, prior benchmarks like Creepy or CCNeg tried to test this, but they had a major flaw. They relied on very rigid, artificially generated linguistic templates. And those rigid templates just fall short because they don't reflect the natural, messy diversity of how human beings actually query systems in the real world. That severely limits our ability to see if a model can truly generalize.
To fix this, the researchers built a brilliant new pipeline. First, they extract positive concepts from existing datasets, like COCO or medical x-rays. Next, they bring in a large language model to propose relevant negative concepts, essentially brainstorming things that could be in the scene but aren't. Crucially, they use an open vocabulary object detector to visually verify that the object is genuinely absent. Finally, the LLM paraphrases the text to create diverse, completely natural-sounding negative captions.
Having diagnosed the problem, let's unpack how they try to solve it in Section 3, a data-centric methodology. The researchers figured out pretty quickly that if your training data doesn't explicitly teach negation, the model simply won't learn it. So they decided to augment the famous conceptual 12M dataset. They injected millions of synthetic negation examples to create CC12M NegCap for standard retrieval tasks. Then they built CC12M NegMCQ, which actually forces the model to do fine-grained reasoning. It makes the model choose between highly similar captions where the only difference is the negation of a single object. We call those hard negative options. Combining these two creates a powerful fine-tuning dataset called CC12M NegFull.
Let's break down the math behind their combined loss function. It's actually really elegant. L_total equals alpha times L_CLIP plus 1 minus alpha times L_MCQ. Basically, L_clip is your standard contrastive loss for broad, coarse-grained retrieval. L_MCQ is a multiple-choice cross-entropy loss that forces that strict, fine-grained reasoning among the hard negatives. That alpha parameter? Think of it as a dial. It lets you balance broad semantic retrieval against strict negation reasoning.
So, the big question, did it work? Let's dive into Section 4, experimental results and insights.
Let's look at standard retrieval first, measuring recall at 5, meaning is the correct image in the top 5 results.
When you test baseline models on standard captions, they do fine, but the moment you evaluate them on datasets with negated captions, there is a massive performance drop across the board. Even models like NegClip, which were explicitly designed for compositionality, suffer up to a 23% drop when faced with hard negatives. It's a huge blind spot.
And honestly, the multiple-choice question task reveals an even starker failure. Standard CLIP models hover right around 25% accuracy on these negation questions. That is literally random guessing. And no, just making the model bigger doesn't fix it. Scaling from a base to a huge vision transformer doesn't solve the underlying issue. Alarmingly, even highly specialized medical VLMs like Conch suffer a 33% accuracy drop when you introduce negation to diagnostic text.
The authors brilliantly diagnosed this as an affirmation bias. Think about it. Because pre-training datasets are overwhelmingly filled with affirmative statements, models get really good at affirmative questions. But when you hit them with pure negation questions, they completely crash. They essentially assume all text is affirmative and just act like the negative constraint isn't even there.
This is the real aha moment of the paper. By using PCA projections to visualize those high-dimensional embeddings, we can see the problem clear as day. Standard CLIP literally maps affirmative captions and negative captions to the exact same space. It treats cat and not cat as identical. Even prior work like ConClip struggles here. It manages to separate positive from negative, but then it just collapses all the negative concepts into one single cluster. So it treats not cat and not flower as the exact same thing. Only text-only models like sentence transformers seem to properly space them out.
Time to put our peer review hats on. Let's move to Section 5, Critical Analysis and Context.
Remember that alpha parameter we talked about? The authors ran an ablation study on it, and the data proves a fundamental architectural trade-off. If you set alpha to 1, relying on the unstandard retrieval loss, your general recall is high, but multiple-choice negation accuracy is poor. Lowering alpha improves the negation reasoning, but it degrades standard retrieval. Basically, with current architectures, optimizing for fine-grained logic actively disrupts the embedding space you need for general semantic matching.
So what's our critical takeaway? Well, the methodology is undeniably effective. It exceeds prior work like ConClip by delivering up to a 28% boost in multiple-choice accuracy. But there's a big lingering limitation. Is the model exhibiting true compositional reasoning, or has it just learned a more complex pattern matching shortcut to beat this specific benchmark? Generalizing to entirely new, unseen syntactic structures remains a really tough open question.
Finally, why does all of this matter outside the lab? Let's wrap up with Section 6, Applications and Future Directions.
This research has profound implications for high-stakes deployments. Take medical AI, for example. You absolutely cannot have a vision language model flag an X-ray as positive just because the clinical report says no evidence of pneumonia. It has to understand the no. Autonomous vehicles have to reliably recognize when pedestrians are not present to navigate safely. And even everyday retrieval systems and multimodal assistants need to strictly obey our negative constraints if we're going to trust them.
Looking ahead, the community faces a massive open problem. This paper beautifully proves that synthetically generated hard negatives provide a great training signal. But relying purely on synthetic data to patch over fundamental architectural blind spots, that's not going to scale forever. We need to go back to the drawing board and design entirely new pre-training objectives and loss functions that inherently teach complex syntactic understanding right from step 1.
Ultimately, this paper's central contribution is proving definitively that standard contrastive learning fails at syntax and providing the community with a robust benchmark to measure it. As the authors put it, pre-training datasets should include nuanced expressions like negation. It leaves us with a really provocative question. Until we design new architectures that inherently understand the invisible, the negated, the things that aren't there, can we truly achieve reliable multimodal AI? Thanks for exploring this fascinating paper with me today on The Explainer.